Okay, there we are. Good morning, guys. So today we are going to continue talking about infinite series. I will give you a couple more convergence tests while I eat scrambled eggs. And we'll solve some problems using these new convergence tests. Last time we talked about the integral test, which is section 11.3. Today we're going to talk about the comparison tests, which is section 11.4. A few little announcement-y things. I did finish grading all of the rewrites for exam 1. So if you submitted a rewritten question for exam 1, those have now been graded, and the exam 1 scores have been updated with that information and finalized. So let's get some of this written down. This is, of course, Calc 2. Today is the 13th. So exam 1 rewrites have been graded. And scores have been updated / finalized. And we talked a little bit last week about exactly what that means. So after I had your exam 1 scores locked in with the rewrite, I duplicated them in the second exam 1 assignment. I'll show you exactly what I mean here. So remember, exam 1 is worth 100 points, and the way that Canvas structured the quizzes, I couldn't make either of these worth 100 points on their own, so you took the test here, and your grade was originally here. And then once I had that grade updated with the material from the rewrites, I copy-pasted the grade here, right? So you should see identical grades under exam 1 questions and exam 1 submit your scanned work for exam 1 here, and that means the gradebook is now completely up to date regarding the first test. There are still some people who have not submitted study guide 1. The purpose of the study guides is never to hurt your grades. I only want them to help your grades. That's definitely the intent, and I'm happy to accept these late. So if you did not turn in study guide 1, please go ahead and do that, and I'll go ahead and get those grades in this week. And that way, as we move into next week, when we'll be doing exam 2, the gradebook will be completely up to date, and you'll know exactly where you stand. If you haven't, please take a look at the comments I left, both under the rewrites and under exam 1. Exam 1, I scanned in all of my written comments that I made as I graded your work. For the rewrites, since there's just one problem each, I just typed them out there in the comment box. Please look at both of those. They're both very important. You definitely want to internalize all of the feedback that I gave you from exam 1 as we move into exam 2. So today, we're going to cover section 11.4, which is on the comparison tests for infinite series. All right. So the comparison tests for infinite series are a lot like, or at least the first comparison test for infinite series is a lot like the comparison test for type 1 improper integrals. It's very intuitive, and I don't think you'll have a whole lot of trouble with it beyond building inequalities. So I don't think anybody will have a hard time understanding the first comparison test. Although working with the inequalities can be a little bit tricky, so we're going to need lots of practice there. The second comparison test is a little bit harder to understand, and you'll have to be careful with your hypotheses and conclusions. So hopefully you've been talking with people a little bit about infinite series, and you're starting to understand a little bit of the notation and the language. I think I just heard my dog bark outside, so I need to go grab him. But then we'll get started. Hey, Andy, I got you, bud. So let's jump right in. So this is kind of our third convergence test for improper integral, or for infinite series. We have the test for divergence, we have the integral test, and now we have the comparison test. And those are in addition to what we know about geometric series and what we know about telescoping series. The first one we're going to talk about here is called the direct comparison test. And it says this: if 0 is less than or equal to an is less than or equal to bn, then sigma from wherever, I'm going to say from 0 to infinity, bn converging implies sigma n from 0 or wherever to infinity of an converges. So if bn is bigger than an and the series sigma bn converges, then so does the series sigma an, right? If you fit in a finite box, if you're smaller than something which is finite, then you have to be finite. And if the smaller guy diverges, then the bigger guy has to diverge also. So very similar to the comparison test for improper integrals. Right? If one series is bigger than the other, then the big guy being finite forces the small guy to be finite. And the small guy being infinite forces the big guy to be infinite. The positivity here is important. Don't forget that. We can only apply this test to series where all the terms are positive. So if your series is not made up of exclusively positive terms, then you can't do this at all. I want to look at a couple examples. So for our first example, let's investigate the convergence of sigma n from 1 to infinity 1 over 2 to the n plus 1, like that. So here the series is adding up the sequence 1 over 2 to the n plus 1. Just to remind you what this looks like, that's 1 over 2 plus 1 plus 1 over 4 plus 1 plus 1 over 8 plus 1, and so on forever and ever. All right, just reminding you what the sigma notation does. If we look at this guy, just the 1 over 2 to the n plus 1 piece, what you notice is that he's always, so this is, let me continue this down here. This is 1/3 plus 1/5 plus 1/9. The next term would be 1 over 17, and so on. This is a little bit smaller than 1/2. This is a little bit smaller than 1/4. This is a little bit smaller than 1/8. This is a little bit smaller than 1/16. So what we're going to do here is we're going to use the direct comparison . And we're going to say, notice that 0 is less than or equal to 1 over 2 to the n plus 1 is less than or equal to 1 over 2 to the n. Why is this bigger than this? Well, because this guy's denominator is bigger. A bigger denominator means you smaller overall. So the denominator of this guy, which is my guy, is a little bit bigger than the denominator of this guy, which means my guy is a little bit smaller than this. And this inequality looks a lot like this inequality. Don't forget the 0 here. This is important. It is true that all of these terms are positive, and if that wasn't true, I couldn't use the test. Moreover, sigma n from 1 to infinity, 1 over 2 to the n, is the same as sigma n from 1 to infinity, 1/2 to the n, is a geometric series. With absolute value of r being the absolute value of 1/2, which is 1/2, which is less than 1. Therefore, sigma n from 1 to infinity, 1 over 2 to the n, converges. Now I like to come back here and name this inequality so I can refer back to it. I name it by just putting a little star next to it. And I can say, thus, by the inequality star and the direct comparison test, my series, the smaller series, sigma 1 from 1 to infinity, 1 over 2 to the n plus 1, must converge also. And that's it, that's job done. So my series is term for term a little bit smaller than this geometric series. This geometric series I know to converge because the common ratio has absolute value less than 1. Therefore, my series has to converge. So Mariano, I'm not working directly with my series. That's the idea. I say that my series is a little bit smaller than this other series. So like this is AN. This is BN. And I say my series sigma AN has to converge because it's smaller than the series sigma BN, and sigma BN is known to be a convergent geometric series. No, that's not correct. So just because the denominator gets big doesn't mean the series converges. Remember, sigma 1 over n diverges. So you're kind of confusing you're confusing the test for divergence with its converse. So just because AN goes to 0 doesn't mean that the series converges. Right? Yeah, so just because the bottom gets big and the top stays the same, that doesn't mean that the series will converge. That just means that TFD will be inconclusive. So we need something a little bit more. Ryan asks if we look for the growing term in the denominator and bn of that growing term in the denominator. Sort of. So the way I chose my bn here is by asking, is there a simpler series? Is this series similar to a much simpler series, a series that I know more about? And what I see when I look at this is that it's not geometric, but if you chopped off that +1, that is geometric. And I know everything there is to know about geometric series. So it's a tempting thing to compare this series to the series I get without the +1. And then the observation is that if you get rid of the +1, you're actually making the thing bigger overall, and the bigger series is convergent as a geometric series. So my series is a little bit smaller than this convergent geometric series, which means my series has to also converge. Simon asked a question that is a little bit confusing in its phrasing. 1/∞ is a heuristic for writing a limit. So if we run let's do TFD on this. The limit as n goes to infinity of an here is the limit as n goes to infinity of 1/2 to the n plus 1 is definitely 1/∞, which is 0, but this is inconclusive. So it doesn't mean that the series sigma an, by inconclusive, i.e. we don't learn anything about the series sigma 1/2 to the n plus 1 from the fact that 1/2 to the n plus 1 goes to 0 as n goes to infinity, right? So just because the bottom goes to infinity and the top doesn't, does not mean that the series automatically converges, right? Think about the series we looked at last Friday, when we talked about the 1/n series, we talked about the integral test. 1/n definitely goes to 0, right? But that series, sigma 1/n, diverges. So what we're getting at here, we're deep enough into series territory now that your mind is going to start confusing sequences with series. They're not the same shit. If the limit of the ANs is 0, then the sequence AN converges. But that doesn't tell me anything at all about the series sigma AN. So this sigma operator says add up all of these things. It's not asking what is the limit of these things, it's asking what happens if you add all of them up. And going to 0 is a necessary but not sufficient condition for the series to converge. Right, so 1/∞ is equal to 0. And that would tell you that the sequence AN converges. But it doesn't tell you anything about the series sigma AN. So you want to, at this point, you want to go back and reread section 11.2. I know that might sound a little bit condescending, but I promise you, I'm not talking down. As we go through these sections, 11.3, 11.4, 11.5, 11.6, go back at least once a week and reread this shit. Reread the definitions. Remember, it's all about partial sums. So in order to keep straight in your head the difference between a sequence and a series, you need to constantly remind yourself the difference between limits and adding things up. Mariana, a sequence converges if it has a finite limit. Remember, the definition of convergence for a sequence is the limit as n to infinity of an exists and is finite. A series converges means something totally different. It means that the sequence of partial sums is finite. When you start adding more and more and more and more and more shit, that starts getting closer and closer to some particular number. So the difference between a sequence and a series is non-trivial. And if you remember, I think one of the problems in our homework last week, one of the first problems in 11.2 is this guy. Yeah, what's the difference between a sequence and a series? What is a convergent series? What is a divergent series? These are very important things to keep straight in your head, and it's very easy to confuse them. So as we go through each of these sections in chapter 11, go back and reread this discussion at the start of 11.2, and make sure you're keeping clear in your head the distinction between sequences and series. Yeah, they make for great true-false questions on the exams. And as we've seen, those true, false, and multiple choice questions can be quite sneaky. There are good true, false questions in here, BT dubs. Where are these? If you look under the review, this shit, right? Come here and look at these. The very first one asks, if the limit of the ANs is 0, is it true that the series sigma AN converges? That's precisely what we're talking about. This is false, right? This is false. If the limit of the ANs is 0, then TFD is inconclusive. We don't learn shit. It means nothing. For the series to converge, we need much more than this. This needs to be true, but also you need more than that for the series to converge. You don't just have to go to 0, you have to go to 0 really, really fast. That's the idea. For a series to converge, the ANs have to go to 0 fast. Okay, so this is the example we just went through. 1 over 2 to the n plus 1 is smaller than 1 over 2 to the n. So since 1 over 2 to the n summed from 1 to infinity is convergent, 1 over 2 to the n plus 1 summed from 1 to infinity must also be convergent. We come back to the DocCam now. So we just saw that sigma 1 over 2 to the n plus 1 is convergent. What about sigma 1 to infinity 1 over 2 to the n minus 1? Focus, you fuck. There we go. Okay. So again, I want to say that this is similar to a geometric series, because if the 1 wasn't there downstairs, it would be geometric. But if you try to build an inequality for the direct comparison test, 2 to the n minus 1 is smaller than 2 to the n. So when you take reciprocals, the inequality flips over. And you get this. So my series is not smaller than 1 over 2 to the n. Definitely it's true that these are positive. But this isn't useful. So my series is a little bit bigger. Not smaller. Than sigma n equals 1 to infinity 1 over 2 to the n. And unfortunately, this isn't useful, right? If you're smaller than something finite, you have to be finite. That's true. But if you're bigger than something finite, you could be finite or infinite. Being bigger than this guy doesn't tell me anything. Yeah. So there's some good questions in chat there. Is there another BN that would work? Could I squeeze this guy underneath some other obviously convergent series? Maybe. Maybe. I don't know. I can't think of one right away, but probably. Probably if you hunted, if you looked very, very hard for the right inequality, you could get this with a direct comparison. But the obvious inequality does not get us there. So really what we want, some other test, some other kind of comparison test. What I want to say is that sigma n from 1 to infinity 1 over 2 to the n minus 1 is really, really close to sigma 1 over 2 to the n. And since sigma 1 over 2 to the n converges, so does sigma 1 over 2 to the n minus 1. That's what I want to say. But I don't have the mathematical tool to let me say it yet. So my series is not smaller than this obviously convergent series, so direct comparison doesn't work. I want to say that my series is very, very similar to that series, because it is. I mean, they're identical. The only difference is that the bottom is off by 1. So I want to say that because my series is similar to this series, and this series converges, so does my series. And the tool that lets us do that is the second comparison test called the limit comparison test. So this is your fourth convergence test for infinite series. Make sure you're keeping track of these. In addition to the regular flow of your notes where you should have this stuff, make sure you have a page dedicated to convergence tests. This needs to be added to that page now. What the limit comparison test says, if sigma from wherever to infinity an and sigma from wherever to infinity bn are series with positive terms, and the limit as n goes to infinity of an over bn is equal to some positive finite number, then sigma from wherever to infinity an and sigma from wherever to infinity bn do the same thing. They converge or diverge together. Kind of like the integral test, right? The integral test says if some things are true, then the infinite series does the same thing as the integral. This guy says if some things are true, then these two series do the same thing. Either both converge or both diverge. So this is our limit comparison test. And I want to go through a little bit of a proof. I'm not going to go through a rigorous proof with you. The proof of the direct comparison test is so trivial, I think it's underneath you. But the proof of this is worthy of a little bit of time. So first, get it down in your notes. Make sure you have this discussion in your notes so you can review it. You'll want to think about why the DCT doesn't work here and why we come up with something like the LCT. And then make sure you have this written down really clearly in your notes. What I mean by converge or diverge together is that they do the same thing. If sigma an diverges, or let's say it like this, if sigma bn diverges, so does sigma an. And if sigma bn converges, so does sigma an. Right, that's how we use this. So if I have a series and I want to compare it to another series, but the inequality for DCT isn't coming out right, that's when you want to use LCT. How do you use it? Well, someone like me hands you a series, sigma an, and I say, tell me whether or not this thing converges. You have to determine sigma bn. You have to pick a series to compare to. And rather than building an inequality here, you're going to ask, well, is there a simpler series, something simpler than sigma an, about which I know more than sigma an? Once you've picked your Bn, you'll take the limit of the ANs over the Bns and see if you get a positive finite number. If you do, then you can conclude that these series do the same thing, which means you then go on to tell me what sigma Bn does and conclude that sigma An does the same. So I'm going to go through a few examples of this with you, and then I'm going to give a few problems and ask you which test should I use and why. First, any questions on the statement of the theorem? Okay. Let's return to this then. I want to investigate the convergence of sigma from 1 to infinity, 1 over 2 to the n minus 1. So Dalton asks, if we apply that theorem, can we show that this series diverges? Let's see. Remember, what's going on in my head is I think this is very, very similar to 1 over 2 to the n. I think that my series is very, very similar to the geometric series 1 over 2 to the n. So I expect this to converge. But let's see. I'm going to run the limit comparison test. First, I have to pick Bn. So I want to pick something a little bit simpler than 1 over 2 to the n minus 1, about which I know a lot. And for me, right now, that's 1 over 2 to the n, right? These guys are very, very close. So sigma Bn is sigma 1 over 2 to the n. And I think that this series is very similar to this series. I take the limit. So now we calculate the limit as n goes to infinity of the an over the bn. No sigmas here. That's the limit as n goes to infinity of 1 over 2 to the n minus 1. That's my an, divided by 1 over 2 to the n. That's my bn. The top and bottom are both going to 0. So I can't just plug in right away. But if I flip and multiply, I see that this is the same as the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. Yes, 1 over 2 to the n minus 1 is bigger than 1 over 2 to the n. That's why I can't use the direct comparison test. That's an answer to Simon's question in chat. So how do I calculate this limit? Who can help me with that? Now the top and bottom both look like infinity as n gets big. Yeah, we divide top and bottom by the fastest growing term. So the fastest growing term is 2 to the n, so I divide top and bottom by that. That's my renormalization trick. And what I get when I do that is 1 over 1 minus 1 over 2 to the n. And now as n goes to infinity, this is 1 over 1 minus 0, which is 1 over 1, which is 1. And this is the number we called C in the theorem. Since C is 1, which is positive and finite, by limit comparison test, the two series do the same thing. Sigma n from 1 to infinity 1 over 2 to the n minus 1 converges or diverges together with sigma n from 1 to infinity 1 over 2 to the n. So the limit comparison test tells me whether or not two series do the same thing. Moreover, sigma n from 1 to infinity 1 over 2 to the n is sigma n from 1 to infinity 1/2 to the n is a convergent geometric series so by LCT, sigma n from 1 to infinity 1 over 2 to the n minus 1 must also converge. Okay, so you're going to have to think about this a little bit. All of this stuff says that the two series in question, sigma 1 over 2 to the n minus 1 and sigma 1 over 2 to the n, they do the same thing. The boxed stuff here proves that this series, my series, and sigma 1 over 2 to the n do the same thing. I then have to go on to say the series sigma 1 over 2 to the n is convergent. We've already shown why that series converges several times, so I'm not showing it here. But it's a convergent geometric series because the absolute value of r is 1/2 is less than 1, right? Therefore, by LCT, since those two series play the same and this series converges, my series must converge also. That is how LCT works. So there are a couple questions in chat here that I want to address. Thomas asks, why does Bn have to be 1 over 2 to the n? Could we exchange the terms, making An 1/2 to the n? So the labels are arbitrary. Usually the series that you're given is the one that we call sigma An, and the series you're comparing to is the one that we call sigma Bn. I don't have any control over the series that I was given, right? I mean, somebody handed me this series and asked me, does this series converge or diverge? So I'm stuck with him, but I get to pick Bn. So because I'm stuck with him, I pick this guy because I think this series is very similar to this series. So in my head, I have a suspicion ahead of time. I say, well, this series looks a lot like the 1 over 2 to the n series. So that's what I'm going to compare to. And then this work says that those series really are very similar. In particular, they converge or diverge together. Finally, I'm able to say, since the series I picked converges and the series I picked is similar to the series I was given, the series I was given must also converge. Dalton also asked a very good question in chat, and that is, do you have to know beforehand what sigma Bn does? Not necessarily. You can go through this work to show that sigma An and sigma Bn do the same thing, and then step to the side and work with sigma Bn. Oftentimes, that's what we do. Now, we have a good collection of series about which we know everything. Geometric series and p-series. So those are your normal basis for comparison. And if you're working with a series and you compare it to a geometric series, or you compare it to a p-series, you shouldn't have to spend much time figuring out what sigma Bn does. But you do need to at least have some little comment, right? So, okay, yeah, this is geometric, and yeah, the common ratio does have absolute value less than 1. So this guy is convergent. So there's got to be a little discussion of what sigma Bn does before you can conclude anything about sigma An. These are really good questions. Gustavo asks, so DCT said that sigma 1 over 2 to the n is similar to sigma 1 over 2 to the n plus 1. Kind of. In fact, what DCT says is that sigma 1 over 2 to the n is smaller than, or sorry, sigma says that sigma 1 over 2 to the n plus 1 is smaller than sigma 1 over 2 to the n. And if you're smaller than something we know to converge, then you converge right away. So that guy was a little bit easier. You may want to go back and rewatch the first few minutes of this video where we did the first DCT. We'll do more. But for now, let's just say that. So DCT, if you can show that a series is smaller than a convergent series, it's convergent. If you can show that a series is bigger than a divergent series, then your series is divergent. LCT, limit comparison test, is for series where you can't figure that out right away, where it's a little bit harder to tell. I've got lots of other examples, but before I go through other examples, I want to prove LCT for you. Okay, so here's again the statement of the limit comparison test. I'm going to push this up here. And we're going to give just a little proof. All right, so suppose sigma An, I'm not going to write the bounds, I'm tired of writing the bounds, and sigma Bn are two series with positive terms. And that the limit as n goes to infinity of An over Bn is equal to C, where C is positive, meaning not 0, not negative, and finite. The statement lim n to infinity An over Bn equals C means that for very large n, what does this mean? So if the limit as n goes to infinity of some shit equals C, that means as n gets bigger and bigger and bigger, this ratio gets closer and closer and closer to C. So for very, very large values of n, An over Bn is approximately equal to C. Right, like A1 million over B1 million should be very, very close to C if this limit is C. That means, or that implies, that An is approximately equal to the constant C times Bn for large n. Thus, the tail, let's say it like this, sigma An is approximately equal to sigma C times Bn, which is equal to C times sigma Bn. And really, I'd be looking here at a tail, so from like some capital N to infinity. For some large number capital N. So the tail of the series sigma An is very, very close to a constant times the tail of the series sigma Bn. Therefore, if sigma Bn, the tail of the series sigma Bn, is finite, so is the tail of sigma An. And in particular, if the full series sigma Bn converges, so does sigma An. And if sigma Bn diverges, so does sigma An. All right, so that's the proof. You heard me use the word tail there a few times. Tail is the term for the end of the series. If you throw away the first few terms, that doesn't affect the convergence. First, any finite number of terms can have no effect on the convergence because adding up a finite number of terms is always finite. So I don't really give a shit about what happens early on in the series. What determines whether a series converges, and listen to this, what determines whether a series converges is not what happens early on, it's what happens late. It's the infinitely many things that can fuck up convergence, not the finitely many things. Finitely many terms can never have any effect on convergence because they're necessarily finite. But if you look at the tail, if you look at the part of the series that goes on and on and on forever, you know, throw away the first 10,000 terms, that doesn't matter. What happened after that is what determines whether the series converges. This limit being finite means that the tail of the series An is very, very close to the tail of the series Bn. So if the tail of the series Bn is finite, then the tail of the series An is finite, right? That's this statement. So if this tail is finite, then this tail is finite. But this tail being finite means this series converges because everything that happens before the tail can't affect convergence. And therefore, if this series converges, so does this series. So by tail, it's not a word I've written down here. You don't need to know what the word tail means to understand this argument, but you do need to read it very, very carefully. The word tail think like a dog's tail. It's the stuff that comes at the end of the dog. Means the terms late in the series. It's a very general word. It's not referring to any specific exact part of the series. Like in sigma from 0 to infinity, 1 over 3 to the n, that's 1 plus 1/3 plus 1/9 plus 1 over 27 plus, and then you go way out here to like 1 over 3 to the capital N plus 1 over 3 to the capital N plus 1 plus 1 over 3 to the capital N plus 2 plus, and so on. This is the start of the series, and this stuff is the tail. So the tail is the general term for the late terms in the series, and usually we say that those are the terms from capital N on. It's just a word that's convenient for describing these things. So you know that the series sigma 1 over 3 to the n is what you get by adding up all of the reciprocals of powers of 3. So it's 1 over 3 to the 0, plus 1 over 3 to the 1, plus 1 over 3 to the 2, plus 1 over 3 to the 4. This goes on and on and on forever. If you chop it somewhere late, then what's left at the end, the infinite string at the end, is what we call the tail. And it's this shit that determines whether or not your series converges. Because all the stuff up here is finite. So you can add it in or you can remove it. It won't affect whether the series is finite or infinite. It's the stuff that comes later on that determines whether the series converges or diverges. And that stuff we call the tail. So like a dog, the tail is at the end. And what LCT says is that if the limit an over bn is positive and finite, then the series sigma an has a tail that is very, very similar to the series sigma bn. And since the tails match, the series converge or diverge together. That's the idea. So I'm gonna bring this down to cover up the definition of tail here because it's not really necessary. And I'm gonna leave this here for a minute so everybody can fill in anything that's missing in their notes. I really want you guys to go over this proof carefully, 3 or 4 times. Talk it through with somebody, right? Especially if you're like back home and your parents or siblings or friends or someone has taken Calc 2 or knows a little bit about infinite series. See if you can explain this to them. See if you can talk through this with anybody. Talk through it with each other. I don't know, you guys have a Discord or something like that where you guys can talk with each other. I'm sure there's something like that. See if you can talk each other through this argument. Try to argue with each other. Try to say, oh no, that part's fucked up, that doesn't make sense, and then force the person to explain why it does. See if you can come up with those explanations, because this will be a really good way to build your understanding of what infinite series are. All right, so just a few more seconds for anybody who's still writing things, and then we'll look at some more examples. So, all right, you guys see Simon posted his Discord in the chat there. I don't have a problem with you guys doing something like that or a group me or whatever. I think it's a good idea. Converse with each other, share ideas, argue with each other. That's the big thing. What mathematicians do, we sit around, we drink coffee, and we tell each other they're wrong. And then eventually, someone convinces you that they're right, and then you write a proof. Let's look at some more examples. Where'd my pen go? Did I really put it back here? Am I that dumb? Okay. Let's investigate the convergence of the sum from n equals 2 to infinity, 1 over n minus 1. Some observations. This is not a p-series because of the minus 1. It's not geometric. It's not going to telescope. So none of that stuff will work. I could use the integral test, but the integral test is a pain in the ass. It takes so long. If we run TFD, the limit as n goes to infinity of the ANs here is the limit as n goes to infinity of 1 over n minus 1. That's 1 over infinity minus 1, which is still 1 over infinity, which is 0. So can I conclude anything from TFD? No, TFD is inconclusive. Caesar asks a good question. How do I know that this isn't telescoping? Because there's no way for these terms to cancel each other out. Yeah, this says not telescoping. So if I had some other factor in the denominator, like n minus 1 times n or n minus 1 times n plus 1, then I could run some PFD and see maybe if this telescopes. But because there's only the one factor downstairs, I know that this can't possibly telescope. So TFD is inconclusive. I don't get anything out of that because the limit of the ANs is 0. Integral test would work. But it takes forever. And I'm lazy. Mathematicians are deeply lazy people. So what will work nicely here is a direct comparison. As n goes from 2 to infinity, 1 over n minus 1 is positive, right? This looks like 1 over 1 plus 1 over 2 plus 1 over 3, and so on. So these are positive terms. Observe that 0 is less than or equal to 1 over n minus 1. That's true. So we do have positive terms. But more is true than that. Also, 1 over n is less than 1 over n minus 1. Because this denominator is smaller, he's bigger overall. So in fact, what we have is 0 is less than or equal to 1 over n is less than or equal to 1 over n minus 1. And this is the inequality that I will label as star. I'll make this a weak inequality so it looks better, it looks more like what you want. Moreover, sigma from 2 to infinity, 1 over n, is a p-series with p equal to 1. So sigma n from 2 to infinity, 1 over n, is divergent. Because 1 is not strictly greater than 1. Thus, by the inequality star and dct, my guy is a little bit bigger than this guy. And when you add this guy up over the same range as my series, you get a divergent series. So by the inequality and dct, the series sigma n from 2 to infinity, 1 over n minus 1 diverges. As you go through your homework, you're just going to be asked to click like diverge or converge, which is so shitty. As you work through those problems, you need to practice writing things out like this. All the words, complete sentences, inequalities, labels, names, references to theorems. You really, really, really need to practice this. So watch how I solve these problems and try to mimic that at first. Jump on Simon's Discord server. I'm gonna pop this open just so I have it saved for myself. And talk with other people about your solutions. Talk with me about your solutions. Share what you're writing and thinking and saying with other folks. So the inequality here is convenient because this is my guy. This is the guy I want to learn about. And since he's bigger than this guy and this guy is divergent, my guy must diverge also. So here, this series is divergent. So rather than trying to squeeze him underneath a convergent series, I want to push him up from below by a divergent series. So I see what you're saying now. It's like last time the inequality pointed in this same direction and we had to use limit comparison. But that's because our series in the previous example was convergent. Here, my series is divergent. So DCT can go both ways. If your series is smaller than a convergent series, your series is convergent. If your series is larger than a divergent series, your series is divergent. So here, the fact that the inequality pointed the other way wasn't a problem. It was actually exactly what we needed. It's a good question, though. It's good things to be thinking about. Other questions or comments on this? So my series is not a p-series, it's not geometric, it's not telescoping, but he is term for term a little bit bigger than the divergent p-series 1 over n. Dalton asked a good question. Does the starting value down here to the bounds ever matter? Nah. Because the convergence of a series is only ever dependent upon the tail. I don't care what happens when n equals 2, 3, 4, 5. I care what happens as n gets towards infinity. I care what happens at the end of the series, not at the start of the series. So what happens at the start of the series will never affect convergence. That's why when I write down those theorems, I'm always starting by writing n equals a, or I say from 1 or wherever, because the starting bounds really don't matter. The only time you can get into trouble there is if I tried to start this series at n equals 1, then that first term would be 1 over 0, and the series would be undefined for that reason. But you will never run into that. So no, the starting bounds, the bounds don't change anything. The upper bound will always be infinity because we're not interested in finite series, we're only interested in infinite series. And this lower bound never has any effect on the convergence. So nope, doesn't really matter. And that's why you see me writing just sigmas without any bounds when I'm getting lazy. So we were given a BN. Yeah, so Ryan asks an interesting thing here about labels. We were given BN and found AN to prove divergence. You could label it like that if you wanted to. Early on, I called my series sigma AN when I used TFD. So here I would still want to call this AN and call this BN. But how you label it is actually arbitrary. So the important thing here is that my guy is bigger than this guy, and the sum, sigma, this guy, is divergent. So the labels AN and BN are arbitrary. And you could say that we were given BN and found AN here. But I would hesitate to do that because earlier I called this thing AN. Do you ever need the n equals x on the bottom instead of just x? So could I write this as just, Fernando asked an interesting question. Could I write sigma 2 to infinity 1 over n minus 1 in place of sigma n equals 2 to infinity 1 over n minus 1? I'm okay with this. This is okay. I don't have any problem with that. If you choose to write it like that, that's fine. Later, we will be talking about power series where there's more than one variable. And in that case, I think it is wise to write this. This is kind of the standard notation. This is what you will see more often. For some reason, everybody likes to write the n equals or I equals or k equals down there. But if your hand is getting sore and you elect to write it like this instead, I got no problem with that. Either is fine. Yeah, sure, go ahead. I got no problem with that. Other questions on this example? I got some more exotic stuff for you then. Let's look at the series sigma n from 1 to infinity sine of 1 over n squared. I'm going to call this S. Another way to save time when you're writing things or to save your hand from getting sore is to give the series a name. And that way, every time you refer back to it, you don't have to write the whole thing. You can just say the series S. Again, it's wise to look at the first few terms. So here S is the sine of 1 plus the sine of 1/4 plus the sine of 1/9 plus the sine of 1/16 and so on. This is a weird friggin' series. None of these numbers are nice. The sine of 1, the sine of 1/4, the sine of 1/9, the sine of 1/16. Since the insides of the sine function are not multiples of pi, these are fucking weird numbers. These are all nasty, irrational numbers. So I really don't have a good feel for what's going on here. In particular, there's no nice way to build any inequalities. So the problem, the issue here, I don't know if sine 1 over n squared is smaller than 1 over n squared, or sine 1 over n squared is bigger than 1 over n squared, or maybe neither is true. It's not at all clear. So DCT is out. Also, the integral test won't work. So DCT, the inequality is hard. I can look at TFD. I can run my test for divergence. Here, the limit as n goes to infinity of the ANs is the limit as n goes to infinity of sine of 1 over n squared, which is equal to the sine of 1 over n squared goes to 1 over infinity. 1 over infinity is 0, so this is the sine of 0, and the sine of 0 is 0. So TFD is inconclusive. The integral test won't work. No good. Because f of x equals the sine of 1 over x. This is, 1 over x squared is not decreasing. All right, you know the sine function oscillates a lot. There's no way to say that this function is always decreasing or even decreasing on any clear interval from 1 to infinity or something like that. So I'm running out of tools. DCT, I don't know how to come up with the inequality. TFD is inconclusive. This series is not a series I can attack with the integral test because the corresponding function is not decreasing. And remember, in order to use the integral test, this function would have to be positive, continuous, and decreasing on the interval 1 to infinity, and it's not. So this is a good candidate for the limit comparison test. That's my only tool left. But I need to pick Bn. Now, if you remember the small angle approximation for sine, so how do I pick Bn? Well, we recall if theta is small, then sine theta is pretty close to theta itself. And as n goes to infinity, sine of 1 over n squared goes to the sine of 0. In other words, 1 over n squared gets very, very small. So for large n, the sine of 1 over n squared should be pretty close to 1 over n squared itself. So we choose Bn to be 1 over n squared. Now I'm going to calculate C as the limit as n goes to infinity of an over bn. That's the limit as n goes to infinity of the sine of 1 over n squared divided by 1 over n squared. Can I cancel the 1 over n squareds? Yeah, definitely not. Right, up here, the 1 over n squared is inside the sine function. Yeah, no, it just doesn't work. Like sine of pi over pi is not equal to sine. That wouldn't make sense. In the numerator there, that's not multiplication, that's function notation. So definitely not. However, the top is going to the sine of 0, which is 0, and the bottom is going to 0. So this looks like 0 over 0, which means we can apply L'Hopital's rule. And if I do that, I get lim n to infinity cos of 1 over n squared times the derivative of 1 over n squared, which is negative 2 over n cubed. And then downstairs, I also have the derivative of 1 over n squared, which is negative 2 over n cubed. And those do cancel. Now, as n goes to infinity, the 1 over n squared that's left inside this cosine goes to 0. And the cosine of 0 is 1. So C is equal to 1. Since C is positive and finite, my series, sigma an, converges or diverges together with sigma bn. Moreover, sigma bn is sigma n from 1 to infinity, 1 over n squared is a convergent p-series. P is equal to 2, which is bigger than 1. Therefore, by LCT, sigma an, which is my series, sigma n from 1 to infinity sine of 1 over n squared, must converge also. And that's the argument done. Okay, so here's all the LCT work. It's actually not bad. if you wanted to, you could start right here. Right? You could start at the choose Bn equals 1 over n squared. Now, how did I know to choose that? I mean, I had this little discussion here for your sake. But really, the solution starts here, and then it's just this stuff. It's pretty quick. Series like this, trigonometric series where the things you're adding up come from trig functions, tend to be hard to work with because the numbers they spit out are not nice numbers. But the limit comparison test will allow us to handle them. Right. So for LCT, you have to pick Bn. So Nazas, we have to figure out Bn. Yeah. Right. So if you're going to run a limit comparison, it's up to you to pick a series to compare against. Here, I chose the 1 over n squared series because I know that sine of 1 over n squared should be pretty close to 1 over n squared itself. Good, good. Yeah, that's the idea. So hopefully a little bit more time, the way of thinking about infinite series will come to you. That's a good idea. I would rewatch each of these lectures at least once. So watch them in class as we do them, and then rewatch them at least once and go back through your notes, fill in any gaps, and you'll understand much better. See, are we running out of time? We're getting pretty close. I would like to do one more example. Let me grab one more out of your textbook. So that's the limit comparison test. There's some examples we did. Estimation, we're not going to fuck with that. Oh yeah, this is a favorite of mine. So, decimal numbers. Show that non-terminating decimal numbers are valid. We had cos 1 over n squared, 1 over n squared supply. So Ryan asked, what if we had cos of 1 over n squared? If you had the series sigma cos 1 over n squared, TFD would do the job. Because as n goes to infinity, 1 over n squared goes to 0, and the cos of 0 is not 0, it's 1. So you wouldn't need limit comparison test for cosine. But if you had tangent of 1 over n squared, the same sort of thing would work. All right, so let's look at what I mean by a non-terminating decimal number, and let's see what I'm saying when we say it's valid. So I'll call the number capital D for decimal, and it's the number whose digits are 0.D1, D2, D3, D4, and so on. Like pi is 3.141596, blah, blah, blah. So D1 is 1, D2 is 4, and so on. I want to show that all the numbers of this form are actually finite real numbers. And the way we can do this is by saying, okay, 0.D1, D2, D3, D4, and so on, that's really D1 times 0.1 plus D2 times 0.01 plus D3 times 0.001, and so on. Right? Because this is 0.D1, this is 0.0D2, this is 0.00D3. So if you add those up, you do get this number. And that is D1 times 1/10 plus D2 times 1/100 plus D3 times 1/1000 and so on, which is d1 times 1/10 to the 1 plus d2 times 1/10 squared plus d3 times 1/10 cubed. You had to do this in one of your homework problems from last week, but there you had a repeating decimal. So d1 was equal to d2 was equal to d3. So Dalton, what I'm doing here is I'm taking something very similar to one of your homework problems from last week, and I'm generalizing a bit. So if you take a number like pi, where the decimals are 1, 4, 1, 5, 9, 2, 6, I could write that, I'll come off to the side here for just a second, 0.141596, that's equal to 0.1 plus 0.04 plus 0.001 plus 0.0005, and so on, which is 1 times 1/10 plus 4 times 1/100th plus 1 times 1/1000th plus 5 times 1/10,000th, and so on. So I'm taking an arbitrary decimal number and I'm splitting it up into its tenths, hundredths, thousandths, 10,000ths pieces. My aim is to show that this series is convergent. So my last step here is going to be to write this as an infinite series. This is the sum from n equals 1 to infinity dn times 1/10 to the n. Now in the homework problem you guys had last week that dealt with this stuff, you had repeating decimals. Here I'm not assuming that the decimal repeats, like pi for example, there's no repetition in there. How could I show that this series converges for every number? And no matter what decimal you started with, it can be expressed like this, and this is always a convergent series. In particular, what can you say about the dn's? It's not geometric. So if dn was a constant, then this would be geometric. But these dn's are not constant, right? Like in pi, the dn's go 1, 4, 1, 5, 9, 2, 6. So I can't like pop this guy out. But there is something I can, good, Thomas nailed it. So I think Nick and Thomas are both getting at the right idea there. Each successive d has less of an impact. And in particular, dn is always between 0 and 9. Because they're digits. So in other words, this will make a nice direct comparison. So I'm going to run DCT. Observe that 0 is always less than or equal to dn is less than or equal to 9, which implies 0 is less than or equal to dn times 1/10 to the n is less than or equal to 9 times 1/10 to the n. And the series of the object on the right, that is geometric. That's 9 times sigma n from 1 to infinity, 1/10 to the n, which is geometric. So even though my series is not geometric, it can be easily compared to a geometric series. It's geometric with the absolute value of r being the absolute value of 1/10, which is 1/10, which is less than 1. So this series, sigma n from 1 to infinity, 9 times 1/10 to the n, is convergent. Thus, by the inequality here, which I'll call star, and DCT, the series sigma n from 1 to infinity dn times 1/10 to the n must also converge. And that's the end. So every decimal expansion is really an infinite series, and all of those infinite series converge. Cool shit, right? This attack is also how you prove that 0.1 repeating is 1/9, or that 0.9 repeating is equal to 1. You just sum the geometric series. And if you haven't gotten to that problem in last week's homework, I'll be looking here in just a minute and clearing all those extension requests. Please do finish that up. We are in this ultra grindy part of the course where you need to have your nose to the stone all the fucking time. If you put in the work now, it'll pay off. The rest of the semester will go smooth. You'll be happy. If you don't, then this is going to be torture. So make sure you're finding, and I mean this literally, multiple hours per day for your homework. Set it aside, put it in your schedule, put an alarm in your phone, do whatever the fuck you gotta do to make yourself sit down and work on problems for a few hours a day. Don't just click converges or diverges. Please, for the love of God, don't use Symbolab or Wolfram Alpha or any of that shit. Don't cheat, it'll fuck you really hard. Sit down and work on this stuff for a few hours a day. If you get stuck, check out that Discord server that Simon posted here in the chat. All right, I want everybody to go and scroll up in the chat to the 1229 thing from Simon, copy that Discord URL. Talk with other people about it. That way you'll get good at this stuff. If you get stuck or if there's something that you're not satisfied, the discussion you can have with the people that are in the Discord thing or that you can talk to in your home life, talk to me. No, the watch it button and the exercises are pretty good. Those explanations tend to be a little bit terse. Sometimes they're good, sometimes they're not. But you want to get to a place where you could explain it to somebody else with confidence. So checking out the little videos that WebAssign provides is not a bad idea. Googling is a great idea, right? If you Google about infinite series, you'll find lots and lots of stuff. So check out some videos that you can find there. If you like to read, you can read by all means, but you'll find lots of videos. Khan Academy I'm not crazy about, but they do a good job. 3 Blue 1 Brown is excellent, but he tends to focus on specific problems. Taylor series, this will be useful later. My favorite is Patrick JMT, right? So he's got lots and lots of stuff. Summation notation, infinite series, test for divergence and geometric series, infinite geometric series. He's got a playlist with all of the infinite series stuff in order. So this sort of stuff, I'll paste this URL in the chat here, is a good idea too. Orgo Chem Tutor on YouTube. I'm not familiar with that, but I will check that out also. But I can definitely recommend Patrick JMT. He does a good job. Check out whatever resources you want to, but the more you spend time working on problems, talking about problems, the better off you'll be. So please make sure you're doing that. Make sure you're putting a few hours every single day into the homework. If you get stuck on anything, don't hesitate to reach out for help. I'll be here. I'll be in an office hour starting right now. So if you want to talk right now, we can do that. Otherwise, I will see you guys in class on Wednesday. All right. So watch for the new homework, wrap up the old one. If you need more time, submit an extension request, please. Check out the URLs that are posted in chat there. I'll give a few seconds to copy those down before I get out of here myself. And I'll see you either in office hours or in class on Wednesday. All right, hope you guys have a lovely rest of your day. That is all.